Hi. Well, it looks like we've made it to Chapter 8. This is hypothesis testing. There's some formal ways that we need to write things down. That's what these first few questions are about. So first of all, test the claim that the mean is. So that is going to say equals. And there's three things we need to write down. One is, what is the claim? And in this chapter, the claim could be about a mean, it could be about a proportion, or it could be about a standard deviation. Once you get Chapter 8 down, the rest of the semester is going to go pretty easy because we're going to do hypothesis testing in different ways, but the main ideas are going to stay the same. So for example, in Chapter 9, it's going to be mean 1 and mean 2, proportion 1, proportion 2, standard deviation 1 and standard deviation 2. So let's get to it. So the claim is about a mean, and then it's is, so it's saying the mean is 12. Oh, excuse me, is at most. At most means less than or equal to. All right, now for what's called the alternative hypothesis, or H1. And H1 can have the symbols less than, bigger than, or not equals. Those are the only three choices for H1. And if this one has an equals in it, then you have to use the opposite. So the opposite of less than or equal is going to be bigger than. So the mean is bigger than 12. And then H sub O doesn't take any thinking at all. H sub O has equals no matter what. And as we go to a full example like number 4, so I'll explain more about why it is you're supposed to set these things up like this. For number 2, the claim is that the mean is over 12. So claim is that the mean over 12 means bigger than 12. And now for H1, like I said, H1 could have one of these three symbols. If this does not have an equals, then H1 just stays exactly the same as the claim. And then H sub O always has equals. And like I said at the top of the page, these can be about means, proportions, or standard deviation. This one is about proportion, so that's P. The claim is that the proportion is, so this one's going to be claim. The proportion is 0.82. Okay, then H1 cannot have an equals. So as I mentioned, there's these three possibilities for H1. Since it can't have an equals, it has to have the opposite. And like always, H sub O just says equals, just always does its own thing. Okay, there's setting up the hypothesis test. Now we'll do a full-fledged example. The claim is that the mean is 33. So we can write down these first three things. Claim is that the mean is 33. And then that means that the alternate hypothesis has not equals. And if I can just go back for a second. Like I said, H1 has these three possibilities. The way that we use this is to tell you how many tails the test has. When it's like this, pointing to the left, it's going to be a left-tailed test. So you draw the bell-shaped curve, but the alpha would only be in the left tail. And then this one would be a right-tailed test. So if I were to finish this one, it would look like it would only have one critical value right here. And whatever the alpha equals, let's say alpha equals 0.05, then it would go in the right tail because this H1 is pointing to the right. And then when it has not equals, well, then it's both left tail and right tail. We call it two tails. So this one, 2 tails. And then h sub o has equals. And this part, h sub o, is used at the end when we do the explanation. Okay, so we've got the sample evidence is n equals 87 people. X bar equals 31.7. And then right here, the S is equal to 1.2. Whenever you're doing a test or a confidence interval for mean, it could be a Z or a T. Well, when it's S that's given, then you use T. So we're going to use a t-test. The next thing to do is draw the picture. The t-distribution, it looks just like the bell-shaped curve. And according to this, it's 2 tails. And if it's 2 tails, that means it would look like this. So these would be the 2 tails. And then the next thing is, if we're using the t-test, then that's table A3. And for A3, we need to know degrees of freedom. Well, degrees of freedom is just n minus 1, so that's going to be 86. And then we need to know alpha. Well, notice that, for example, here too, I said test the claim, but I did not say use 98% or 99%. Whenever that percent is left off, then you just assume it's 95%. That means that the alpha is equal to 0.05. Okay, so now for table A3. So, as I mentioned before, when you use this test, you have to decide, is it 1 tail or 2 tails? Ours is 2-tailed. And what's the alpha? 0.05. Next, we go to degrees of freedom, which is 86, and I'm pretty sure they're not going to have an 86. The choices are 80 and 90. So you have to use whatever's closest. Doesn't matter if you round up or round down, just whatever's closest. Since our degrees of freedom is an 86, then it's best to use 90. So that would be 1987. So in here, I would just scratch that out and say I had to use 90. And then this would be 1987 for this critical value. And then it's symmetric, but this one is negative 1.987. Okay, there's the critical values. And now for the test statistic. Well, the test statistic is T, but the formula is just like the Z formula. You take the score, which is 31.7, minus the mean, which is 33, divided by the standard deviation of 1.2, but then that was based on 87 people, or goats, whatever they were. No, it was people. Didn't mean to disrespect the goats, sorry. And then you divide by the square root of 87. As I mentioned before, you need to put this in parentheses and put this in parentheses. Calculator. So we've got parentheses 31.7 minus 33 divided by parentheses 1.2 divided by the square root of 87. So it's equal to a negative 10.105. So I was supposed to get this, and I was supposed to get these. Now, I also want you to be aware that you can use the calculator to do that last formula. So you would go to Stat, move over to Tests, and now that we're doing hypothesis test, that's these first 6 things right here. So right now, for this example, we're using the t-test. You tell it, so this is saying if you look at h sub o, that's why it has that o there, what's the mean? And then the mean was 33. Then the sample mean was 31.7 with a standard deviation of 1.2 based on 87 people. This makes it two-tailed, and then calculate. So you'll notice that it gets the same negative 10.105 for the t, as well as it tells you what the p-value is. So this would be an extremely small p-value, which basically says if you were to reject what they say, which is what you're supposed to do here, because this negative 10.105, it would go past the negative 1.9, in fact by a lot. So that means you would reject. You would say, this is not true. Does it equal 33? No. That does not equal 33. And 87 people was enough evidence to prove this is wrong. So the claim is false. So that would be the whole hypothesis test, but I didn't ask for that on number 4. Just the critical values and test statistic. Okay, number 5 is going to be a full-fledged example of hypothesis testing. So out of 90 people, so that's my sample evidence, n equals 90 people, x equals 8 had served on a jury. So then I could just divide those two numbers to find out what percent is that. So that's called the sample percentage, or the p hat. So simply divide an 8 divided by 90, and it is 0.089. So 8.9%. Okay, next, test the claim that less than 10%, so that's a proportion. The claim is that the proportion is less than 10%. Since that doesn't have an equals, then H1 is just like that. And that's pointing to the left, so that's going to be a left-tailed test. And then, like I said, H sub O always has equals, no matter what the other guys have. And then I can draw my little bell-shaped curve right here. So once again, I did not say what to use for the level of confidence in this problem, so use 95%. That means alpha equals 0.05. And since it's left-tailed, then 0.05 goes right here. And then we need to find the critical value. Well, since it's on the left, I know the critical value is negative, but what I've got to do is use the table A2, because whenever you're dealing with a proportion, no matter if it's a claim or a confidence interval, it's going to be a z. So we need to be using the negative z-scores. And then this is the left tail, so this is 0.05 for us. So then you just look through for what's closest to 0.05. And there's actually a tie right here. The star tells you to look down at the bottom, and it says if you were looking for 0.05, then the z-score is negative 1.645. Okay, we're almost done. Next, the test statistic is going to be z equals. So in the last one, I did the formula one time for fun, but I really would expect you to use the calculator. So here we go. You go to Stat, move over to Tests, and then look down the list. Which one could it be? Well, it's that one right there, number 5. One proportion, a z-test. We need to tell it what's the number for H sub O, that is a 0.10. How many successes, so that's X, 8, out of how many? 90. So be aware that, I don't know, I usually write down the n first and then the x, but the calculator has it the other way around. So make sure you put it the way they want. X is 8, n is 90. And then this should be pointing to the left. And then calculate, and it turns out that z is negative 0.351. And then the question is, does this number right here land in the critical region? Or in other words, here is this line in the sand that says if it goes past that, then I've actually proved something. But if it doesn't go past that, I don't really have enough evidence to prove anything. Well, a negative 0.351, so 0 would be in the middle. Negative 3.51 would land about here. So that means that we didn't actually prove anything. So formally that's called fail to reject. In other words, we did not have enough evidence to reject H sub O. Or we cannot make a conclusion. So basically there's a lack of evidence to prove anything one way or the other. And what else have we got? So I just skipped over to here. Test the claim that there's a typo, that the mean is 100. So the claim is that the mean equals 100. H1 cannot have equals, so it has not equals. That makes it two tails. H sub O always has equals. And then I would write down the information n equals 50 people tested. They had an average of 103.6, and the sigma is equal to 15. So this is one of the few times when we have the sigma. That means that it's going to be a z-test. So the z-distribution looks like this. It has two tails, and alpha is equal to 0.05. So that means you have to take the 0.05 and cut it into two pieces, so 0.025 on this side and 0.025 on this side. Then the critical value here, the critical value here. So since we're doing a z-test, that's table A2. So I could just get this one, the negative one, and then this would be the same number except positive. So if I use the negative table and I look for 0.025, it's right here. They have it exactly. Then you look to the left and it says it equals negative 1.9, and you look up, it's a 6, negative 1.96. On the other side, positive 1.96. Next, for the test statistic. So that's going to be a z, and we can use the calculator. So if you go to stat and tests, there it is, the very first one is z-test. So it was a claim about 50, it was a claim about 100. The standard deviation sigma is 15. The x bar was 103.6. The the sample size is 50 people were tested. This makes it two tails. And then calculate. The z equals 1.697. So then we're trying to see, does a 1.6 go past a 1.96? And the answer is no. It lands about right here. So that means that, again, failed to reject, we're not able to prove anything. And this, not being able to prove anything, basically happens for two main reasons. One is the sample size was not big enough. So perhaps it was that 50 is not enough people. Or it could be that the difference between what the claim is and the 103.6, there just isn't that big of a difference. That's basically what this is saying, that there really isn't that big of a difference between these two if you're going to base it off of just 50 people. But watch this. If I did the same thing, but I based it off 500 people, so let me just quickly go back and go back to the z-test. All I need to change is one number. What if this was based on 500 people? Then calculate, and now the test statistic is a 5.3. So if this was a 5.3, it would go way past this, and then you do have enough evidence. So that's what these formulas and this procedure is saying, is with all of this as your evidence, is that really strong enough to reject this 100? With 50 people, and this being a 103.6, it's not. And then something about the standard deviation. So in here, I included some extra information because there's times when people read a question and they say, oh, I'm not sure if it's about the mean or the standard deviation. I'm not sure what I'm supposed to do. But just concentrate on this. So I skipped all the rest and just went to this. Test the claim, the standard deviation. That means that you don't even need this information, because that's not a standard deviation. That's not a standard deviation. This is a standard deviation. This one says the standard deviation is supposed to be less than, so this is key, this you keep, but this is just extra information you don't need. Okay, so test the claim that the standard deviation is less than a 0.3. So the claim, standard deviation overall is less than a 0.3. H1 is allowed to have a less than, so that stays the same, making it a left-tailed test. H sub O, always the same, equals. And then the only sample data I have is that there were 80 drinks, so that's N equals 80, and that the sample standard deviation was a 0.5. Then draw the picture. The picture for chi-squared is a little bit different. Because it's squared, it does not have any negatives. It starts at 0. And then it's skewed to the right. This one is going to be a left-tailed test, so this is where I would put the critical value. And once again, I did not say to use 98% or 95%, so we're going to use 95% as the default. So that means that this is 0.05. And then, since it's chi-squared, we're using table A4. So here's my table A4. Basically, this is a 0.05. That means that this would be a 0.95. When you're using this table, the right tails are on the right and the left tails are on the left. So we have to be using the left side of the table. But up here, none of these say 0.05. That's because the 0.05 is on this side, but it matches up with this one, the 0.95. So we're supposed to be using this column right here on the left side. So we also need degrees of freedom. So that's going to be n minus 1. So that's going to be 79. Degrees of freedom equals 79. Sort of doubt that they have 79. We'll probably end up using 80. So again, it's this column, and then go down, and sure enough, they don't have 79. We have to use 80. So the critical value is 60.391. And then for the test statistic, it's going to be chi-squared this one is not in the calculator. So this one, though, is pretty small. The formula is pretty easy. It's chi-squared equals n minus 1, or in other words, degrees of freedom. And then you take the s squared divided by the sigma squared, where this is this s, and the denominator comes from this sigma. So in this one, it's going to be degrees of freedom, which is 79, times the s 0.3 squared. Oh, sorry, I looked at the wrong one. 0.5 squared for the s, and then the sigma 0.3 squared. And then we need to calculate that one ourselves. So a 79 times 0.5 being squared, and then divided by a 0.3 being squared. It equals 219.444. So if you look at our graph, this is the critical region between 0 and 60, and if you're going to be able to prove anything, then this has to fall into the critical region. But does the 219 land between 0 and 60? The answer is no. It would land over here. So we've got a fail to reject. And once again, we proved nothing. Boy, I hope we're able to prove something pretty soon. And then on to a little bit of basketball. So for the last 36 basketball games, keep in mind that this was filmed in January of 2014. So this was true at least in January of 2014. Kevin Durant of the Oklahoma City Thunder averaged 29.5. He was the leader at that time, or at this time, with a standard deviation of 6.5. So we've got the sample evidence. N equals 36 basketball games, averaging 29.5 points per game, standard deviation 6.5. So test the claim that Durant could be as good as Kobe Bryant. So could be as good as, we're going to have to change that into either an inequality or an equation. And for Kobe, his lifetime average is 25.5. So it's going to look like this. The claim is about a mean, and the mean is for Kevin Durant. Is he as good as Kobe Bryant? Well, to be as good as someone is not that you're better, it's not that you're worse. So it's not that it's bigger, not that it's less than, it's that it's equal. So this is for Kevin Durant, based on these 36 basketball games. Is his lifetime average possibly equal to 25.5 for Kobe Bryant? Looking at the numbers, it sure looks like we're going to be able to reject and say, no, actually Kevin Durant is better. Let's see. Then H1 is going to be not equals, which makes it two-tailed test. And then H sub O has equals. Next up, it could be either a z-test or a t-test. When it's about means, it's either a z-test or a t-test. And it all depends on this. Because this is an S, then it's a t-test. So that is A3. And for A3, we need degrees of freedom, which is 35. It's a two-tailed test. We're going to use 95% as the level of confidence, which means 5% is alpha, and then you have to cut that in half. So 2.5% on each side. And then for table A3, as mentioned before, you have to decide, is it one tails or two tails? This one is two tails. And the alpha equals 0.05. By the way, the other way you could look at it is, if you only looked at one tail, it has 0.025. So if you only looked at one tail, it has 0.025. So that means you have to use the middle column, either way. And this was based on 36 basketball games, so degrees of freedom will be 35. And if we're using the middle column and 35, then the critical value is 2.030. .030. On this side, it's negative. And then for the test statistic, that's going to be t equals . It was a long problem. Look at that. It took me right down to the edge of the page. T-test. So, the good old t-test. Let's see. The claim is that he's as good as Kobe Bryant, 25.5. Kevin Barnett, actually 29.5 with a standard deviation 6.5. This was based on the last 36 basketball games. And then, calculate. Yay! We proved something! 3.692. Does that go past a 2.0? Yes, it definitely does. So we actually proved something. So in conclusion, what you say is, okay, whoever said these two guys are equal, they're wrong. So reject H sub O. In other words, it's false. Whoever said the equals is false. So they are not equally good. More specifically, we're talking about points per game. And then you could go on to say, in fact, if you look at this, Kevin Durant seems to be better than Kobe Bryant.